Okay, so in the previous few lectures, we have looked at diodes. We have looked into different applications of diodes as well. Namely, we have looked into how to use a diode so that you can make the current flow in only one direction. So we have looked into applications such as rectifiers, half-wave rectifiers, and full-wave rectifiers. We have also looked into clippers and clamper circuits as well, which were discussed at the end of the previous lecture. Now, starting today onwards, we will be discussing a different device called a MOSFET, a metal oxide semiconductor-based field effect transistor. And you'll see that this is the device that is being used predominantly today in the entire electronics industry. So whatever you have in your pocket, maybe an iPhone, maybe an Android, you're using your laptop or any other smart device, everything is built off this device called the MOSFET. So we are going to learn what is there inside a MOSFET that makes it interesting, what are its properties, and how to make it useful in any kind of circuit. So of course, all the digital circuitry in the devices that you are using, that's built using MOSFETs. Most of the analog circuitry that you are using in your day-to-day life, that are also mostly uses this kind of a device. Okay. So what we are going to do today is that we are going to learn a little bit about the physics of the MOSFETs and also what kind of equations do we use, what are the characteristics of this MOSFET that makes it useful and that makes it interesting for any kind of circuit development. So that's what we are going to learn today as well as in the next lecture. All right, so we are going to look at the physical structure of a MOSFET, that how do you build a MOSFET. We have already looked into PN junction diodes. And there we know that if you have a P-type semiconductor and you have an N-type semiconductor, you put them side by side, you form a PN junction diode. Of course, there will be some junction built-in capacitance and junction built-in voltage that we have looked into. We have looked into the depletion region formation in a diode as well. So we'll look into how to build a MOSFET physically. Now, one thing that we could have done is that because we have discussed diodes, we could have discussed BJTs first. Because what BJTs or bipolar junction transistors are basically two PN junction diodes which are placed very close together. So you may have heard about PNP or NPN type BJTs or bipolar junction transistor. So if you have a PNP, that means you have a P to N junction and then again N to P junction. So again, I guess this does not work really well. We have to get some new markers. All right, so but you get this point, right? You have a P, then an N, then another P. So you have one junction from P to N, and then another junction from N to P. That's what a PNP BJT will look like. Similarly, an NPN BJT will look like the reverse. You have N, P, and N. But we are not discussing BJTs right now. We'll come back to BJTs toward the end of the course because we'll discuss a lot of different properties of MOSFETs and how to make this MOSFET useful in an amplifier circuit or a filter circuit. Basically, what we are going to learn is what is there inside this op-amp that you have learned in the last 10-15 lectures. And we'll see how to build an op-amp using MOSFETs. And once we do that, we'll come back to the concept of BJTs. And we'll see how MOSFETs and BJTs, in terms of their applications in circuits, are very similar, even though the device fabrication or the properties of the device will be very different. But we'll try to map it in terms of the application because we are doing circuit design in this class. We are not really learning about device physics. But in terms of circuit applications, MOSFETs and BJTs will have a very similar kind of applications, and that's what we're going to see later part in this course. But what we are going to start now is on this topic of MOSFETs, and this will probably continue for next 15 or 20 lectures, or maybe at least next 15 lectures, because MOSFETs will have a lot of different things to discuss about MOSFETs. That how to understand the properties of the MOSFETs, how to DC bias it, how to analyze it in terms of AC signals, and so on. How to build an amplifier, how to build a single-ended and differential amplifiers, and then eventually an op-amp. So that would probably cover the next 10 to 15 lectures at least, and then we'll come back to the concept of BJTs. Okay. So today, what we'll start with is the physical structure of a MOSFET. But even before going there, we are talking about transistors. We are talking about 3 or 4 terminal devices. Your diode was a 2-terminal device. You just had the P and the N. Now, the main difference between a diode and a transistor is that the transistor is considered as a device which has 3 to 4 terminals. Sometimes you'll see that in books it's written as a 3-terminal device, but sometimes you'll see people telling you about the fact that it is a 4-terminal device. So why do you have this dichotomy? It's basically because you generally need 2 terminals from the current for the current to flow from one place to another, right? So if you have one terminal over here and the second terminal here, you can sort of already understand that if I make a current flow between terminal 1 to terminal 2, I can do that, right? So that's the use of these 2 terminals, terminal 1 and terminal 2, which will be called the drain and the source of the MOSFET. What are these other terminals? So there is one terminal called the gate, and that gate terminal, the job of the gate terminal is to control the current amount of current flow. In the diode, you had a voltage applied across the diode and you had a current across the diode. There was not much way to control, or there was not much you didn't have not much option to control the current through that diode or the voltage across the diode. It was determined by the other components in the circuit. But here, in case of a MOSFET, you can control how much current you want to flow through the device by providing a gate voltage or a control voltage. Why does it call the gate? Because again, from your diode concepts, you know that you can use a diode as a gate. You can open the gate, you can close the gate. Here you can control the gate, that how much amount you are going to open the gate or by how much amount you are going to close the gate. So you have more control than a 2-terminal device over here. Okay. So the current will flow from one terminal to other. The third terminal will be the control terminal. So what is the 4th terminal here? The 4th terminal is actually defined as the body or the bulk. And what is the meaning of the body or bulk of a device is that you're going to build this particular transistor, a 4-terminal device, on a silicon wafer, for example. So you cannot really buy you can definitely buy one single transistor, but you'll see that the transistor is big, but the actual device that makes the current flow possible through it is very, very small. This is in the range of micrometers or maybe even nanometers with today's technologies. So you cannot really buy something and hold in your hand a nanometer sized device or a micrometer sized device, right? So that's extremely, extremely small. So what is done today is that you build hundreds and thousands of these devices on a platform. Let's say on top of this table, we are creating we are trying to solve let's say a kid's puzzle, and we are putting all the pieces together on the table. So that's what you do when you do a circuit design, that you take many of these transistors and you put them in certain configuration on top of a platform, and that platform is called a silicon wafer. I can bring 1 or 2 silicon wafers maybe in one of the later lectures to show you how it looks like. But the purpose of having a wafer is that you'll build multiple, maybe millions of these devices on top of that wafer. And when you are building millions of those devices, you need a platform. You cannot have individual devices which are, let's say, numbered 1 to a million, and each one of them is micrometer size, right? So you cannot really do that. You know how hard it will be, because most of you have already worked on breadboards and PCBs, right? You are now miniaturizing it into micrometer or nanometer scales. Okay, so that wafer will basically be your body or the bulk. And one terminal of the device needs to be connected to the body. We'll come to that, why it needs to be connected to the bulk or to the actual body of the wafer. But that is the 4th terminal that sometimes people do not talk about. So generally, you'll see that the books write that the MOSFET is a 3-terminal device. Then they're talking about the drain, source, and the gate. But if it says that it's a 4-terminal device, then you're talking about the body or the bulk as well. And it is also an important terminal of the device. Even though not as important as drain, source, and gate, that it's important enough. All right. Now, in terms of the control, right now we are just talking about a black box. As you see here, I've just drawn a black box. And the control terminal, if it is a current control terminal, and if the device is controlled by a current, then it's a BJT, it's a bipolar junction transistor. And again, we'll come back to what bipolar junction transistors look like and how we can control them. But right now, it's important to note that the BJT is a current control device. On the other hand, the MOSFET is a voltage control device. So at the gate, you'll apply a voltage and you'll get a current. Now you already learned from your op-amp or amplifier analysis that your input could be voltages and currents. Your output could also be voltages or currents. So in this case, what you have is a voltage controlled current source, because your gate is a voltage and eventually you'll get a current from terminal 1 to terminal 2, which will be a function of the gate voltage. So this device eventually becomes a voltage controlled current source. Similarly, BJT is a current controlled current source. Okay. All right, now how does this device look like? How does the metal oxide semiconductor field effect transistor look like? You'll build this transistor on a wafer or using a bulk semiconductor that we already talked about, that you need a large platform on top of which you'll build multiple devices. The device actually looks only like this much, that you have a source, you have a drain, and you have a gate. And we'll come to that. What does source mean? What does drain mean? And what does gate mean? But let's say you have these three terminals: source, drain, and gate. But the source, drain, and gate is built on top of a silicon wafer, right? So, and that's the body terminal. That's where you connect the bulb or the body terminal of this device. And as you can imagine now, that this body terminal, and right now I'm showing just only one device, and the p-type silicon below that device. But the p-type silicon extends on the left side and extends on the right side as well. So what you really can have is maybe a long p-type silicon or a p-type wafer, and on top of that you build these small devices. Let's say this is the source, drain, this is the gate. Again, you can build another device over here: source, drain, and the gate. Again, a third device here: source, drain, and the gate. Okay, so you can build multiple devices on the same bulb or on the same wafer. Now, what we are showing in the next slide is basically we are cutting this entire. Let's say you cut the entire wafer along these two lines. Okay, so now you get the source, drain, gate, and some body or bulk beneath the source, gate, drain structure, right? That's what we're showing here. But this p-type silicon extends on the left side and the right side in a real physical fabrication of this device. Okay, now this is just a cross section. So this is called a cross section of the device. So this is the side view. In fact, it's a 3D structure. And how would the 3D structure look like is, again, if you extend all of these source, drain, gates, and all other things on a third dimension. So let's say if we're thinking of the 3D structure, so let's just increase this on the third dimension, and the source will be extended like that, the gate will be extended like that, and the drain will also be extended like that. Right? So this is how the 3D view of the structure would look like. Now, if you look from the top, let's say you're looking from the top, your top view will look like something shown on the right-hand side. So this is the side view on the left-hand side of the 3D structure. And on the right-hand side, what you see is the top view of the same 3D structure. Now, on the top view, what you see is the gate in the middle. This is the gate. And for the source and drain, you can have one contact. You can also have multiple contacts like this. So these are just multiple contacts shown to the source and the drain. So on the top view, there is one contact over here. There is another contact over here on the source. And on the drain, there is one contact here. And then maybe another contact over here. And that's what you are seeing from the top. That you are seeing the gate and you're seeing the contacts on the source and the drain. So that's how the side view and the top view looks like of this 3D device. And again, keep in mind, this entire wafer is basically a 3D structure. So everything can be extended like that. And you can create the entire 3D tree. So this is how the gate will look like. If you're making and I'll come to what this dimension means, but this is how the gates will look like. And again, if you have contacts on the source and drain, they will also look very similar to this top view that you see over here. Now you'll see that when you are discussing about MOSFETs, people will tell you about the lengths and the widths of a MOSFET. What does the length and the width mean? The length basically means the length of the gate. So in this case, even though like it's being shown as the width here from left to right. But by definition, this is called the length of the MOSFET. That what is the distance between the source and the drain regions, or what is the length of the MOSFET. The width is defined in this direction. So this is basically called the width of the MOSFET. So this is how you'll define the length and the width of a device. And depending on the length and width of the device, you'll see that you can change the amount of current that flows through the device. So I guess the definition of lengths and widths are clear, because this will be very important when you learn or when you solve any problem about MOSFETs, that what is the length and what is the width. The length is the distance between the source and the drain terminals, whereas the width is basically the dimension of the MOSFET in the third dimension. That's the extended dimension that you don't see in the side view. Right? So in the side view, it's easy to define only the length, but it's not very easy to define the width, because the width is the extended. So this is your length, but the width is something that you extend your gate, and then the extension, the amount of extension that you have on the third dimension, that basically becomes your width. So on the top view, it's very easy to see what is the width and what is the length, but from the side view, we'll only see the length of the device. Now, why is it called the source and the drain, the two terminals? You already know that the gate terminal is called the gate because it helps you to gate the amount of current, and it in fact helps you to open the gate or close the gate by a specific amount, so that you can let a particular amount of current flow through the device. Right? So you have yes, questions. Yeah. Okay, exactly. So that's a great question. So I think since it was already drawn, I should talk about this width. So this width is sometimes if you take a fabrication technology class for a MOSFET, how to actually fabricate this device, you'll see that there is a concept of active area, that you dope a certain area of the device, and then you start creating the source, gate, and the drains. So if the area is not doped properly, so for example, this is P-type silicon, right? So the region where you have this P-type doping, that's called your active area. That's where you're going to create your device. The gate can be extended a little bit on both sides of that active area. So the pink region is called the active area, and the width of the active area, eventually, this extension is very small. This is probably a few nanometers or so. But the overall width of the pink area, that's what you should be concerned about when you are designing a circuit. Right? So, but this is an exaggeration of how the MOSFET device looks like. This extension is probably not that much. It's probably only a few nanometers, very small amount, and that's why the width of the gate area and the width of the active area would be very similar in a real device. But the length of the gate is eventually the distance between the source and the drain regions. Now, the next question is, why is it called a source and why is it called a drain? As you know that the device lets current flow from one terminal to another. And these terminals where the current will flow between is the source and the drain. Now, the source would be the source of the current carriers. So, of course, your current carrier could be an electron or it could be a hole. If it is an electron, the source is basically the source of the electrons. And drain is a sink for those electrons. So the electrons will flow from the source to the drain side. And even if it is a hole, the hole will flow from the source to the drain. So that's the meaning of the sources and the drains. That the source will be the source of electron or the source of hole. And depending on that, we'll have two different types of MOSFETs. One will be the N-type MOSFET and the other one will be the P-type MOSFET. That's there in the next slide. But before going there, I wanted to make sure that you guys know that what do we mean by source and what do we mean by drain. Now, again, coming back to the name, it's called a metal oxide semiconductor field effect transistor. So, of course, first of all, why is it called a transistor? Because the first time when people developed this three-terminal device, that was, I think, almost in 1946, 1947, that time frame. and it was developed here in the US in the Bell Labs. And when they first time created this device, that was used to transfer a value of resistance at the gate from a different value of a resistance between the drain and the source. In fact, they created a BJT, so that's a bipolar junction transistor. So they wanted to transfer the resistance from one side to the other side, and that's how the name came about, that it's a transfer of resistances as well. And you know it from your op-amp discussions as well, right? There is one particular transistor at the input side, the output side, one particular resistance at the input side, the output side resistance could be different. For example, for an op-amp, the input resistance is infinity, the output resistance is 0. So using that device, you are transferring a value of resistance X to another value of resistance Y. So that is something we can do using these devices as well. So the first use of these devices were in the field of transferring one resistance to another. So that's how the name came about, that it's the transfer of resistance, and that's why it's called a transistor in short. Why is it called a field effect transistor? That's because you have a voltage applied at the gate to control the current flow between the drain and the source. As you're applying a voltage at the gate, you are creating an electric field. So this is a field effect transistor. On the other hand, BJT is a current control transistor, whereas the MOSFET is a voltage control transistor. As you're applying a voltage, you're creating an electric field. That's why it's called a field effect transistor. And why is it called metal oxide semiconductor? That comes to the structure of the gate. So this gate terminal is a metal. So this is metal. And then in between, you see that there is a yellow material. That's an oxide, or silicon dioxide to be exact. And then under the silicon dioxide, you have silicon. So you have a metal on top, that is the gate material, the contact material at the gate. Then you have an oxide, which is an insulator. And then you have a P-type silicon, which is a semiconductor. So that's why it's called a metal, followed by oxide, followed by semiconductor, FET. Okay. Now, another thing that you can already probably relate with whatever you have learned using op-amps is that if I'm applying the voltage at the input of the MOSFET, now in this case, the input is the gate terminal, because that's why you apply a voltage to get certain amount of current between the two output terminals. So if you apply a voltage at the gate, you'll see no current flow into the gate. And why is that? Because in between the gate and the semiconductor, there is an oxide insulator layer. So this yellow region is oxide, which means it's an insulator. It does not conduct current. So whenever you apply a voltage at the gate, no current will go through the gate. So that comes back to your understanding of the op-amps, where we talked about the fact that there cannot be any current flow in the input terminal of the MOSFET. Because the input terminal of the MOSFET, as you'll see, eventually goes to the gate of input terminal of the op-amp, eventually goes to the gate terminal of the MOSFET. So that's something we'll see when we discuss the internal structure of an op-amp. All right. Now coming back to N-type MOSFET and P-type MOSFET. What is the difference between N MOSFET and P MOSFET? For an N-type MOSFET, your body or the bulk will be a P-type silicon. So that's something that's just the opposite. So why is it the opposite? Because using the N-type MOSFET, what you're trying to create is current flow from the drain to the source. Why I'm saying current flow from the drain to the source? Because you already know that the source is a source of electrons and drain is the sink for the electrons, or the drain for the electrons. Now, if electrons flow from source to drain, the current will flow from drain to source, right? Because current flows in the opposite direction of the electrons. So that's why you'll see that for an N-type MOSFET, the current will flow from drain to source. For a P-type MOSFET, the source is a source of holes, because when you talk about P-type or positive type, what is positive, electron or hole? The holes are the positive types, right? So for positive type MOSFET, you're talking about holes. So the source will be a source of holes. And since there will be a flow of holes from source to the drain, the current will also flow from the source to the drain. So flow of charge carriers for P MOSFET are the holes. And as the flow of charge carriers happens from source to drain, the current flow also happens from source to drain for p-type MOSFET. For n-type MOSFETs, the charge carriers are electrons because N stands for negative. So these are the negative type MOSFETs, which means the charge carriers are also negative type. And from the source to drain, you'll have the flow of electrons. If electrons are flowing from source to drain, the current will flow from drain to source. So as you see, in terms of current flow, the N-type MOSFET and P-type MOSFET are the opposite. For N-type MOSFET, the current flows from drain to source. For P-type MOSFET, the current flows from source to drain. Or yeah, so any questions over here? So that's the flow of the current. Now, in terms of the flow of the carriers, it's the same for the N-type MOSFET and the P-type MOSFET, because source is the source of the carriers. So if your carrier is an electron, which is true for N-type MOSFET, the carriers will flow from the source to drain. If you consider a P-type MOSFET, your carriers are the holes, which means that they will also flow from the source to drain. So in terms of the carrier flow of the carriers, it's not different, it's the same. The carriers always flow from source to drain because source is where they are being originated, the drain is where they are going. But in terms of the current flow, it could be opposite. It will be opposite in an N-channel MOSFET versus a P-channel MOSFET. Now, what is called a channel? The channel is basically the area through which the carriers are flowing from source to drain. So the channel is the region below the gate through which the carriers are flowing from source to drain. Now, as that there are multiple different types of MOSFET. There is enhancement type MOSFETs. There are depletion type MOSFETs. What we will be interested in the course and what the entire semiconductor industry is interested in are something called the enhancement type MOSFET. In an enhancement type MOSFET, the channel itself is of the opposite type of polarity or the opposite type of semiconductor as compared to the source or drain region. So in the source or drain regions, for an N-channel MOSFET, you'll have N-type silicon because the source is a source of electrons. So it has to be N-type silicon because in N-type silicon or N-doped silicon, you have an excess of electrons. Right? If it is P-type silicon, you'll have an excess of holes. And that's why for P MOSFET, the source and drains are P-type silicons. So if the source and drain are of N-type silicon, the bulk is for an enhancement type MOSFET is of course opposite type, and in this case it is the P-type silicon for an N MOSFET. For a P MOSFET, the bulk of the body becomes the N-type silicon, and you create the channel through the bulk or through the body in between the source and drain region just under the gate. So that region is called the channel. And now how that channel is formed, so there is an entire theory behind it. We'll look into it in small details, but it will be covered in further details in your device physics classes, that how this channel is formed between the source and the drain regions. But for now, this is how the device looks like, that there is a source region, there is a drain region, there is a channel in between, and the bulk will be the opposite type of silicon as compared to the source or the drain. The symbol of this looks like this. So that's how the symbol of a MOSFET looks like. And in this case, this is an N-channel MOSFET. So as you see the left-hand side, you have an N-channel MOSFET, which means that the source, drain, and the channel region are N-type, whereas the body or the bulk is P-type. And the direction of this arrow will always be on the source, and it will be in the direction of the current flow for the MOSFET device. So in this case, because this is an N MOSFET, the electrons will flow from source to drain, which means the current will flow from drain to source. So the current will flow out of the source. That's why the direction of the arrow is flowing out of the source. The arrow will always be on the source, be it an N MOSFET or a P MOSFET. So if we look at the P MOSFET symbol, for the P MOSFET, the source is the source of the holes, which means that the current will flow from source to drain. That means current will flow into the source of the device. That's why the arrow is pointing inward at the source. So that's what the P MOSFET symbol looks like, that the arrow will point inward at the source. For an N MOSFET, the arrow will point outward from the source, because it will always show the direction of the current flow in the device. In an N MOSFET, the direction of the current flow is drain to source, so it will flow out of the source. For a P MOSFET, the direction of the current flow is from the source to drain, so the current will flow into the source. Now, what does the dashed line indicate over here? The dashed line actually indicates that it's an enhancement mode MOSFET. Now, I have talked about it briefly that this is an enhancement mode MOSFET or enhancement channel MOSFET. There is another type of MOSFET available, which is called the depletion mode MOSFET. In a depletion mode MOSFET, the channel is already created, that if you have an N-type source and an N-type drain, there will be a channel which is already created in between the source and the drain, which is also N-type. For enhancement mode MOSFETs, you do not create a channel separately. So what happens, we'll discuss this more, but what happens is that as you apply the gate voltage, the electrons get attracted. So let's say if you apply a positive gate voltage, your gate voltage is more than, let's say, some threshold voltage. What will happen is that because this is a positive voltage, electrons will get attracted from the bulk or from the body towards the region which is just below the gate. As you are attracting more and more electrons, the P-type silicon in between the source and the drain, that gets converted to an effective N-type silicon, because you have more number of electrons now which are attracted toward the gate. So this is called an enhancement mode MOSFET. That's the difference between depletion and enhancement modes. And generally, again, we'll not go discuss depletion mode MOSFETs because you don't use them in industry anymore. You only use enhancement type MOSFETs, which we'll be discussing in today's or like in the next lectures as well. So what enhancement MOSFETs mean is that you do not have a channel which is created even before the application of the gate voltage. Only after the application of the gate voltage, the channel is formed. That's what enhancement mode MOSFET means. And that's why you see that these are dashed lines over here, which means that there is no direct connection between the drain and the source. If it would have been a N-type silicon all throughout, you would have a direct connection between the drain and the source. But in an enhancement mode MOSFET, you will not have a direct connection between the source and the drain. But as you apply a gate voltage, you will attract more electrons from the bulk area. So the electron concentration below the gate will increase, and that will form an N-type channel from the source side to the drain side all throughout. So that's the meaning of your enhancement mode MOSFETs. So again, P-type, you have the similar symbol. The only difference is that the current will flow into the source, because current flows from source to drain in this case. And in digital circuits, you'll see that sometimes the P-type MOSFET, instead of showing the arrow, they'll show it with a bubble on the gate, which just means that you need to apply a negative voltage, a negative gate voltage at the gate to create the channel. And why is that? That's because for a P-type MOSFET, the source and the drain are P-type silicon. That means you have an excess of holes. But in between the source and the drain, you have the N-type silicon, which means you have an excess of electrons. If there is an excess of holes on the left side, excess of holes on the right side, but an excess of electrons in the middle, then you cannot have a continuous current flow from the left to right? Because the sources or the holes in the source of the P-type MOSFET, they will be recombined with the electrons which are below the gate, and that means there will be no current flow. Electrons and holes will destroy each other. Right? You need to have a fixed amount of current flow. For that, you need to have a continuous flow of the same type of charge carriers. If you don't have that, there cannot be any current flow. So from source to drain, it has to be the same charge carriers that are flowing through from the left side to the right side. And in this case, because you want to create your flow of current using holes, which are positively charged carriers, you need to attract more holes from the body to the region which is just below the gate. That means you have to apply a negative voltage at the gate so that you attract more and more holes, which means that there would eventually be an excess of holes just below the gate. And if you have an excess of holes at the source, if you have an excess of holes at the drain and excess of holes in the channel, eventually you have the same type of charge carriers all throughout. And that's when you can get the flow of current. But if there is an excess of holes in the source region and excess of electrons in the channel region, as you are trying to make the holes or electrons flow, they will destroy each other because electrons and holes will recombine and eventually you will have nothing. So that's why to form or to make sure that you have flow of current, you have to apply either a positive voltage or a negative voltage at the gate, depending on whether you have an N-type MOSFET or a P-type MOSFET. And this is called an enhancement type MOSFET because by application of that voltage, you enhance the properties of the device and you in fact change the properties of the device so that you get a channel in between the source and the drain which was not present before. So you enhance something by application of the voltage, and that's why it's called an enhancement type MOSFET. Now, where are these used? As I mentioned in the beginning of the lecture already, that it's used everywhere. In all the electronic devices you are using today, all of them are using these MOSFETs as well as BJTs in some cases in those devices. So if you look into the circuit board of an iPhone, there is an RF front end, a radio frequency front end, which is receiving the signals from when you receive a call or when you're surfing the internet. And that RF front end contains analog modules for communication, and those are made of MOSFETs. The power management unit, which basically from your battery of your iPhone or the battery of the Android device, you are creating the required amount of current required for all those devices. So you need some kind of a power management unit. And that power management unit is made of MOSFETs as well as BJTs. So we'll discuss BJTs later on, but the power management unit is a place where you have both MOSFETs and BJTs, and that's a predominant use of BJTs today in any kind of circuits. You have a memory, which is fully made of complementary, and we'll learn what complementary MOS means, but this is made of MOSFETs. You have a digital processor, which is again purely made of MOSFETs. So as you see that, as you break down this device, or as you break down the iPhone, you'll have these different areas where the MOSFET and BJT devices will be used. So we briefly talked about CMOS or complementary MOS. Now, what complementary MOS means, complementary MOS digital technology, what this means is that you have a PMOS and you have an NMOS together. And we'll discuss more about this in later, but when you have both PMOS and NMOS circuitry together, it's generally called CMOS. Now, in CMOS digital, this top region is called a pull-up circuit, and this bottom region is called a pull-down circuit. In this case, the pull-up circuit is made of only one PMOS. The pull-down circuitry is made of only one NMOS, but there could be more number of transistors. We'll discuss more about digital devices and digital circuits later on in the course, and we'll know how to design the CMOS digital devices or CMOS digital circuits. But what this device is doing is that you have a PMOS on top, you have an NMOS on bottom, and you can apply a input voltage at the gate. Now, how do I know that the top device is a PMOS? Because as you see that the current is pointing inwards. And you always know that the arrow will be at the source. So this means that the source is on top for this device and the current is going into the source, current is flowing out of the drain. So which means that this top device is a PMOS. For the bottom device, the current flows into the drain and flows out of the source. Because electrons flow from source to drain, that means current will flow from drain to source. So the pull-down network or PDN, that is always made of N-type devices, and pull-up network, that is always made of P-type devices. And when we discuss about CMOS digital circuits later on in the course, we'll see why is that. That why do you have pull-up devices as PMOS and pull-down devices as NMOS. Now, this circuit is basically an inverter or a NOT gate, as you know. What it does is that if your input is a high value, if it is a digital 1, it converts that digital 1 at the input to a digital 0 at the output. And if your input is a digital 0, it converts it to a digital 1 at the output side. And how does it do that? As we already discussed, that you need to have a positive gate voltage, or in fact, as we discuss more details about the MOSFETs, you know that the gate to source voltage has to be positive for a N-type device. So if you have an NMOS, the gate to source voltage needs to be positive for the current flow. Now let's just imagine that this point's voltage is 5 volts and the ground is of course 0. Okay, so as you are applying 5 volt to the gate of the NMOS device and the source is connected to 0, what is the VGS? What is the gate to source voltage? So this is called VGS or V gate to source for the NMOS device. So how much is the gate to source voltage in this case? 5 volts, because gate is at 5, source is at 0. If you have a positive VGS for the NMOS device will turn on. Why? Because as you apply a positive VGS, if you're and in this case, like we were not going into the full detail, we are just saying VG is more than VTM or some kind of a threshold voltage, but your VS was already mentioned as 0. So basically your VGS is more than some threshold voltage. And in that case, you attract electrons from the bulk and you eventually form the channel. You also attract electrons from the source and drain regions as well to form the channel. So as you apply a positive voltage, you form a channel and then only the current can flow. The device can turn on. So as you apply a positive voltage over here, the device can turn on. So that means whatever, so if you have stored some amount of voltage over here, you will have a current flow through the device, and eventually, because you can treat this MOSFET also as a switch, that okay, if I apply a high amount of voltage at its gate, the switch will turn on and there will be a current flow. What is the property of an ideal switch? That it will have zero resistance and the voltages at both sides of the switch will be same. So the output voltage will be same as the voltage at the source side. The drain voltage will become same as the source voltage, which means the output voltage will become 0. So if you apply a high voltage, a 5 volt at its gate, the output will become 0. And while at the same time, for the PMOS device, what is the VGS? The input is 5 volts. The source is connected to VDD, the supply. Let's imagine that's also 5 volts, which means that at your gate, you're applying 0 voltage, not a negative voltage. You needed to apply a negative voltage at the gate so that you have a current flow through the PMOS device. So which means this PMOS switch is off when you are applying a 5 volt at the gate. So if you have a 5 volt at the gate, your device on top is open, then you have your output over here, and device at the bottom is shorted to ground. So what will be the voltage at the output? It will be equal to the ground, right? So that's why if you apply a 5 volt, a high voltage at the input, your output will be equal to ground. And ground is at 0 volt, that means your output is at 0 volts. Similarly, if you had applied a 0 volt at its input, let's say you apply 0 volt at the input side. If you apply 0 volt at the input side, what is the VGS of the NMOS? The NMOS will have a VGS of 0 because gate is at 0, the source is also at 0. So gate to source voltage is 0. The NMOS will not turn on. It will not turn on as a switch, which means that the output will be disconnected from the ground. But what is happening on the top side? Your gate voltage is at 0. Your source voltage is at 5 volt. That means with respect to the source, you are applying a negative voltage at the gate. Your gate to source voltage is minus 5 volt for the PMOS. And when you apply a negative gate to source voltage for the PMOS device will turn on because the PMOS device will attract, as you have this negative voltage at the gate, it will attract more and more holes from the N-type silicon or from the bulb, and then you'll form a channel from the source to the drain region. So the PMOS device will turn on, which means that the output will be connected to the VDD. Right? So the output is directly connected to the VDD as you apply a 0 volt at the input. So as you apply a 0 volt at the input, your output will be 5 volts. And that's why it works as an inverter. Your input is 0, output is 5 in terms of volts. If your input is 5 volts, your output is 0 volts. So we look at the characteristics of the MOSFETs, and again, as we looked into the characteristic of the diodes, we found out what is the diode current and diode voltages, right? The same thing we'll do with the MOSFET. We'll look at the IV characteristic or current voltage characteristic for the MOSFET, and we'll take a look at two different approaches. One is called the energy band approach, and one is the mathematical model-based approach. So we'll look into these two methods in detail in the next lecture. but I wanted to get started with some of the definitions that we'll be using and eventually how the MOSFET IV characteristics will look like. And if you plot the drain to source voltage of the MOSFET on the x-axis and the drain current of the MOSFET on the y-axis, assuming that you have enough voltage at the gate to turn the MOSFET on, assuming that the MOSFET is already on, the amount of current that flows through the MOSFET also depends on the drain to source voltage of the MOSFET. So the ID versus VDS characteristics looks like this. It has two different regions. One region where the current increases almost linearly with the voltage. So that's called the linear region or the resistor region, because the MOSFET works like a linear resistor. It just works like a resistance that you apply a voltage across it, you get the equivalent amount of current. Okay? According to Ohm's law, something according to Ohm's law, that your current will be almost linearly proportional to the voltage that you apply across it. Because the voltage applied across the device is the drain to source voltage in this case, that's your x-axis. Assuming that the gate is already at a potential, already at a voltage that the MOSFET is on. Right? So this is an N-type MOSFET, so you'll apply a positive VGS, so your gate is at positive voltage, your source is at a negative or a zero voltage, so that you have a positive VGS, and then you can attract more electrons from the bulk towards the area which is just below the channel, so that you can form this continuous channel from the source to the drain region. Okay. That's how the MOSFET device will work. Now, if we assume that we have already done that, even then, the current through the MOSFET will be a function of the drain to source voltage of the MOSFET. And this is called the output characteristics, because ID is an output quantity, the current is the output quantity of the MOSFET, and the drain to source voltage is the output voltage of the MOSFET, the voltage across the device. Right? So that's why both voltages and currents are at the output, which means that this is the output characteristic of the device. And in the output characteristic of the device, there will be two regions. One is the triode region where the device will work almost like a resistance. And then there will be a region, you'll see that this is very interesting, that the current almost saturates. As you are applying more and more voltage across the device, the current through the device does not change. And that makes it different from any other device that you have learned in the past. Resistors do not have this property, capacitors, inductors, diodes, none of them has this property, that even though you're applying a large voltage across it, the current through the device remains constant. So in this region, it becomes a current source. So if you want a source, if you want a current source that provides a fixed amount of current, this is your device. That you apply a particular amount of gate voltage, you make sure that the device is on, and then you get a fixed amount of current, even though the drain to source voltage can change. So that's the biggest property of this device that makes it unique as compared to anything that we have learned before. And this region is called the saturation region. Why? Because the current is already saturated. So you have a saturated amount of current, irrespective of how much drain to source voltage you have for the device. However, why am I calling it the gate controlled current source? Because as you apply different amount of gate voltages, your amount of saturation will be different. So you may get a curve that looks like this, a curve that looks like that, maybe a curve looks like this. And in this case, so let's say the topmost curve that I just drew, in this case, the VGS is maximum. So whatever maximum volt VGS that you applied, that's over here. And this is corresponding to the VGS minimum, that you have the device turned on, but still the voltage value is small. Maybe the voltage value is 2 volts. This is 2 volt VGS. Let's say this is 3 volt VGS. This is at 4 volt VGS, and this is at 5 volt VGS. So you have different values of VGSs, and according to those different value of gate to source voltages, your current, the saturated amount of current can be different. So it's a gate controlled current source, that by controlling the gate voltage, you can control the amount of current that will flow through the device, but it will be independent of the amount of voltage that is applied across the device from drain to source. So that's the biggest property of a MOSFET that makes it interesting and unique as compared to any other device we learned before. Now in the next lecture, we'll do an energy band treatment of the MOSFET, and we'll try to see how we come up with this kind of IDPD characteristic. Okay, that will do from the energy bands, and we'll also do it mathematically to show the mathematical equations that determine the characteristic of the device.